tutorial. Okay, so let us continue that in this class also about second law of thermodynamics. Okay, so this is problem number 4. With today 3-4 tutorials, the tutorial problems upon second law of thermodynamics would be completed. In tomorrow's class, certain problems are still remaining upon first law applicable to control volumes, like transient problems. Okay, means unsteady problems. Those are very easy actually. That's what I have skipped them. But anyhow, in view of all students, so next class I also would be teaching that. Okay, so this is today's problems. We have 3 interesting problems. Fifth problem is much interesting and lengthy. So please solve the problem number 4 as soon as possible. Then let us go to the fifth problem. Okay, so here we have 2 different choices. Okay, fuel A, fuel B, but however, both the fuels are behaving differently. Okay, so whatever the maximum possible temperature we can obtain here for the fuel A is 2200 Kelvin. Okay, whereas for fuel B it is very less, it is 1200 Kelvin. Okay, but fuel A, the calorific value or heat releasing rate over here is 30 megajoules per kg. For fuel B, it is 40 megajoules per kg. Okay. The cost also certain difference is there. Okay. So now when you are using certain reversible cycle over here, okay, then which fuel you would be choosing? That is the question about. So I hope somebody has already solved. Can anyone tell me the answer? If you have solved already. Okay, so yesterday I have uploaded Sontag textbook solutions. Okay, so problems. Anyhow, you have you might have soft copy of Sontag. Then solution manual also I have uploaded. Okay. So even exercise problems also you can solve by yourself easily because solution is given over there. Yeah. So practice very well and that would be very helpful to you in your exam. Along with that, Professor Subramanian Roy also has provided you certain link. Okay, please follow that link and you can find some more problems. Okay. So let us see solution of this problem. Anyone solved about this? Okay, let us see here. The fuel A. Anyhow, we are considering this is the efficiency. Okay. Everything is at low temperature for both the cases is 350 Kelvin. Yes. So from this what we can take, the efficiency we can calculate by assuming this is the reversible cycle and also by assuming maximum work is extracted. Okay. So this is the 0.84%, 0.84 means 84% we are getting over here. Okay. Along with that, QA you know because the fuel calorific value is given that is 30 megajoules per kg. Yes, that is this. When you multiply with efficiency, you are getting this. Okay. And with price when you are calculating, okay. So this is the energy releasing per dollar. Okay. So similar way, we are going with second choice of fuel B. This is very simple problem actually. And here in the similar fashion, we are calculating over here. And this is giving you 28 megajoules per kg work. Okay. But however, when you consider this in terms of energy release rate per dollar, okay, it is coming under like this 21,000. That means 21 megajoules per dollar. In that case, what would you consider? Fuel B would be very much economical for you, is it? So this is very simple problem. How are we considering and calculating in terms of the price and uh, selecting certain fuel? Okay. So now this problem is quite interesting and this is very lengthy also. Once you practice this problem very well, then handling all thermodynamics equations of this particular chapter, okay, and even writing the code in the ES. This code is a bit lengthy, okay. So you can practice very well. I am going to show you the solution as well as ES code for this problem, okay. Yeah, please try to understand and try to solve this problem by yourself. Okay, 5 minutes is not sufficient, but still try to understand what are the problems you will be using. What are the formulas actually, not problems. So if somebody writing code in ES, that would give you results faster. Anybody trying for that? Okay. So what is this? This is the Carnot cycle. Okay. So with two isothermal processes and two adiabatic processes. Okay. Initially, the steam is at 40 watt pressure. Okay. And the quality of 15%. Then it is expanded upon the turbine to a low pressure of 1.5 watt. Okay. During that time, 491.5 kilojoule per kg specific work is extracted. Here, you are asked to draw cycle with PV coordinates. Okay. And also, at all the points, since this is the Carnot cycle with four processes, we have 4 points. Okay. 4 states, we can say. At all the states, you need to calculate properties as well as all the process, you need to calculate heat and work. Okay. That is, then finally you need to calculate the efficiency. Okay. So the first part and last parts are so easy. Okay. But B is very lengthy process. Okay. It covers all calculations in one problem. Let us see. So this is your cycle, is it? So this is water actually. Your working substance is water. That means steam. It is operating between two pressures, 40 bar and 1.5 bar. Okay. Here this is initially at 40 bar pressure and 15% of dryness fraction, and that is heated in the boiler. It has been reached to stage 2, means saturated vapor. That saturated vapor is expanded upon the turbine in the adiabatic process. There we have obtained this much of work. Okay. Then here the condenser is connected. Okay. Phase change has been happened over here. Okay. And then this liquid is, means this is certain dryness fraction is involved over here. Okay. Liquid phase as well as vapor phase. Then that is pumped back to the this thing, boiler. Okay. The problem with the Carnot cycle is these all actually we will be discussing when we are discussing about Rankine power cycle particularly. Okay. But now also I would like to say, if you want to run your thermal power plant, okay, on the Carnot cycle, then your cycle should be included in this, within this domain. Okay. So because of that, you have to pump this partial phase like liquid as well as vapor. That is highly difficult. Okay. That is highly difficult. Since here we are going just up to saturation stage. Okay. Then whenever you are expanding upon the turbine, here moisture content is very high. Yes. Okay. But that is not desirable. So why cannot we go superheated? Means this is the constant pressure as well as constant temperature. Okay. Our Carnot cycle itself is demanding the constant temperature process, means isothermal process. If you go over here in view of this point, okay, if you go over here, then that process itself would not be isothermal process because temperature would be increasing over here. That is the reason when you are following thermal power plant, whatever this cycle, according to the Carnot, that will be included over here only. Okay. So anyhow, these all let us discuss at the end. At the end means there is one separate chapter for the power cycles. Okay. As per this particular problem, this is our cycle. Okay. We have added it over here. Fine. So now let us shift to the process B. There is so much noise, right? Here some construction work is going on. Okay. This is now process 1-2. The process 1-2 is what? Isothermal process. Yes. Okay. So here what are we doing over here? The work we can calculate with PV. Okay. And our total energy equation is like this. Okay. So here we are considering enthalpies over here. Okay. The Q equal to H2 minus H1 we are considering over here. So now V2 from the table, you can get this. What data you will be using to get this particular V2? 40 bar pressure and saturated vapor. Okay. Then what is this? This is the specific volume. Okay. V2 you can get like this way. Then even for this point, okay, saturated vapor and 40 bar pressure, from the table you can get this enthalpy also. Okay. Fine. Simultaneously U2 also, means internal energy. Now V1 actually V1 is with certain dryness fraction 15%. Okay. So that's what, if you want to calculate V1, you need to look in the table. this VF, and anyhow VG is this only. Yes. So VF also you will be finding out. VF means what? Specific volume of saturated liquid at 40 bar pressure. Okay. And then like this way, we will be calculating V1. Then in the similar fashion, we will be calculating our H1 also. Okay. These are all the data, whatever. This VF value, this HF value, these all you have to look in the table. Okay. Then now we are, by using this particular formula H2 minus H1, this H2, H1 here are specific enthalpies, means per kg involved over here. In our problem, it has been given 2 kilograms, is it? So that's what we are multiplying with 2. Okay. This is your heat addition in the process 1, 2, because that is the constant pressure heat addition process in the boiler. Right? This work is very minimum. Okay. So when we are calculating with the volume change, okay. But here actually, when you see in the sorry, PV diagram of Carnot cycle, then you can understand both the variations, how volume also changing. Okay. Now for process 2, 3, since it is adiabatic process, heat transfer is completely zero. Okay. And work we are extracting over here, that is given in the problem itself. Okay. So, but that work is anyhow, the specific work has been given, simply multiplying with your mass. So that way you have obtained this. Okay. Now, at this point, we are getting U3. Okay. X3 and H3. Fine. But pressure, you need to calculate these all according to the, again, you need to use your heat balance equation over here. You will be equalizing them. From that, you will be calculating this internal energy, and this is the parameter of reference. Then you will be going at that particular pressure. Okay. That way you will be calculating. This is actually, you need to do so much of exercise, okay, by yourself manually. Anyhow, this total problem, let us see in EES, that time you will be understanding very clearly. Process 3-4. Process 3-4 is what? Constant pressure, heat reduction process in the condenser. Yes. There again, we are calculating in terms of enthalpies. Okay. How can we get these enthalpies? First, you need to have idea about this thing, right? H4. Okay. H3 we have calculated over here anyhow. You need to have idea about H4. But here we don't know dryness fraction again. So that is the reason what are we doing? By using the extreme limits, Q supply, this is heat rejection by heat supply, equal to low temperature by high temperature. We are considering over here the ratio. That means what? Efficiency equal to 1 minus QC by QH. Same time, the efficiency equal to 1 minus TC by TH. Yes, that we are using over here. Okay, that way we are calculating this particular thing of Q34. Okay, and that we are equalizing to H4 H3 minus H4 of this H3 minus H4. H3 we know over here. Okay. Then H4 also calculated. From the H4, once you know H4, at this point, from your data table of 1.5 bar pressure, saturated vapor enthalpy, you know, saturated liquid enthalpy, you know. Now H4 we have calculated here by following this certain procedure. Okay. So that way you can calculate your X4. Okay. Once you calculate X4, then you can calculate V4. Again, this is saturated liquid specific volume. Okay. With whatever the procedure even. This is the X4 value, and this is the saturated vapor specific volume minus saturated liquid specific volume. Okay. These are the formulas that you have to practice very well. Okay. Then same time we can calculate in the similar fashion U4 also. Okay. So that way we have calculated anyhow Q34. Process 4.1 means pumping back to the boiler. That is adiabatic process. So heat transfer is 0 over here. Okay. Work involved is U4 minus U1. Okay. Now we know about V4. Just now we have calculated over here. Okay. V1 internal energy at 0.1. Pressure we know that is 40 bar pressure. Okay. Dryness fraction is already given in our problem itself, 15%. Okay. So with that we have calculated. This is your work. Okay. The efficiency is like summation of total work by heat input. Heat input is happening in case of process 1, 2. Okay. At the beginning only we have calculated this. And whatever all 3, 4 process, whatever work output is there, those all works we have added. That way we have obtained this particular efficiency. Okay. So now the problem I would like to solve by EES. Okay. Then that would be how will you solve? You can see, and even the same solution also I will be giving to you. Let me open the problem. So anyone has tried to solve this? Can you please let me know if you have already solved this problem in your EES? So what all are given to you? Like P1 given, P1. Okay. So this problem actually if you solve manually, it will take very long time. If you solve through ES, it is very easy for you. That is 40 bar, right? 40 multiplying by 100 because we need to represent over here in kilopascal. Okay. And even in temperature is in what? Here temperatures are not given anyhow. Fine. Okay. That is P1. There X1 actually, X1 given in your problem, that is 0.15. Fine. Okay. Then P2. This P1, P2 both are same, right? That is constant pressure heat addition process in the boiler. Yes. So that is the reason P2 also 4000 given, but still X2 is the saturated vapor. That is the reason we are putting over here saturated vapor, that is 1. Okay. And then P3 and P4 both are P3 equal to 150 means 1.5 bar. So 150 kilopascals. P4 also equal to 150. Okay. Then what is given? W what is the 23? Yeah. W23 is given. That is specific work actually. 491. Yes, sir. Also mass flow rate is given to you. That is 2 kilograms. Yes. This is the data available with you. Okay. Now everything according to the code only. Let us see. At the point 1, let us calculate our H, our specific volume. H1 equal to enthalpy with the steam, comma, P equal to P1, okay, comma, X equal to X1, okay. So now let me check. Yeah, okay, this is the data so far we have given. To P1, P2, P3, P4 are these pressures, X1.15, this is our data, and H1, okay, H1 is how much? H1 is 1344. I think H1 we have calculated at the end or here in the next slide. Yeah, H1 not calculated, but anyhow, if it is needed or not needed, okay, that is another issue. Let us calculate everything. V1 equal to volume, okay, and then in P1, okay, and then let us consider this H only, okay, at this enthalpy, H equal to H1. Okay. Then let me check again. Okay, so now V1 we have added. If we calculate V1 anywhere, yeah, V1. V1, where is it? Yeah, V1 here. Do you able to see my slide? This is very small actually. V1, it is there here. By using dryness fraction, we have calculated. Okay, after this much of lengthy formula and all, this value we have obtained over here. Okay, fine. Then what shall we do? Then like that, H equal to, I'm copying this. Okay, here instead of X1, I'm giving X2. Okay, and then enthalpy. Enthalpy at 2 is 2810. Is it matching? Yeah, 2810 here. Okay, 2801, sorry, 2801.44. This is also 2801. Nice. Then let us get the temperature also. What is happening over here? Okay, T1 equal to, that may or may not be required. Let us get all the properties, no problem. Picture. Where shall we get? Here let us take. Here let us take. Okay. But anyhow, that is saturation, right? Means latent heat process, means constant temperature, constant pressure. Okay, where is this table? It is gone. Yeah, here. Okay, so what we have entered over here, temperature, right? Yeah, it is temperature. Okay, so any question? Somebody's mic is on. Okay, okay, this is 250.4 degrees centigrade. Okay, so you can go and check with your tables at this particular pressure, what is the saturation temperature. Okay, that we can get over here, and then what can we do? Now Q12 we need to calculate, right? We have calculated here Q12, is it? That is simply mass multiplying H2, we have that, minus H1. Yes, this is only the formula we have. Okay, that is giving you here upon upon this data solution. Okay, this is Q12 means heat supply 2913. Is it matching? Yeah, 2914. Okay, fine. And then what we need to do here? We need to calculate work also here. But for that, we need, that is the PB work, right? So we need V2 also. V2 equal to, okay, V2 equal to then volume let me take this. Then again run. Where these are going? I don't know. Okay, and then what it is giving to you? V2 is 0.04978. Is it matching? V2 0.04978. Okay, exactly. Okay, and then what can we do? W1 2. W1 2 are we calculating? Yes, sir. It is 1 and also mass multiplying and then minus 1. Okay, so let me check. This is the data, right? Okay, so this is we are getting over here. Okay, that is fine. Then now we need to calculate U2. Okay, U2 equal to internal energy then okay, then P equal to P1 comma X equal to X2. Okay, that is the internal energy we can get. Okay, no need to check, obviously we will get. Then U3 we need here, U3. Okay, for U3 what we have done? Okay, here some calculation missing, right? This is what process is this? Adiabatic process. Adiabatic process means Q0. Then it is work equal to delta U. Is it? Work equal to delta U. In that case, U3 minus U2 equal to W. Is it? W23. Yeah. That way only we got our U3 over here. U2 we know and W we know. Since this is 0, according to the first law equation, delta U equal to W. Okay. So that we are doing now. U3 equal to U2 minus W23. Okay, that is the reason here actually I have not extended a explanation over here. Okay, so now you can get your U3 over here. Let me check that. Yeah. Okay, so where is your internal energy table? This is your internal energy table. U2, how much here? U2 2602. Okay, and U3 2111. U3, where do we have here? Yeah, U3 2111. Okay, matching, it is matching very well. Fine. Okay, now what we need to calculate more? Then obviously this has certain dryness, right? Dryness fraction. This also has certain dryness fraction. Let's calculate X3. X3. How would you calculate X3? You need to give independent properties, right? Quality, yes, and then substance is steam, and then we know that operating pressure as the P3, P equal to P3, okay, and then U equal to U3. Anyhow, that point is representing 3, right? U3. Okay, fine. Let me calculate X and C. Oh, what is the error? Improper property indicator encountered, valid property encountered. What is this? What is the error here?
You have missed comma, I think.
Where? Okay, fine.
Please.
Thank you. Yeah. Let me check now. Yeah. So now your X3, okay, X3 is giving in the table, right? Since we have given this matrix form. Okay, where is X3? Yeah, X3, 0.801. Is it matching with our problem? Yeah, this is the 0.801. Okay, fine. Okay, and then what we need to calculate that? And then let us, here V3 we have calculated, right? V3 and H3 also required. H3 not calculated, right? Okay. V3, H3, let us calculate. V3 equal to volume V equal to V3. Now X equal to X3, let us take. Okay, fine. Then yeah, what is it giving? What we are looking for? V3, yeah, 0.9289. V3 is matching. Yeah, 0.9289. Okay, 0.929. Okay, fine. Okay, so then what we need over here more? H3 we need to calculate. Okay, H3 equal to enthalpy, and let us consider this point only anyhow. Fine. Okay, is it giving you back? Okay, so enthalpy of 2250. Enthalpy of 3, yeah, 2250. Fine. Okay, and then now what we need to calculate? All we have calculated over here. Yes, and then we need to calculate. Anyhow, if for at the end C is about the efficiency, right? That is the reason. Let us calculate temperature also over here. Temperature equal to P3, okay, and then X equal to X3 also we can take. Okay, enthalpy we can take, or this also we can take. Let me run again. Okay, fine, no problem. So temperature is 111.3. Okay, that is these temperatures actually we have not calculated in our theoretical problem. Okay, here we are getting them. But anyhow, that is the saturation temperature only. You can get from your table, steam table also. Okay, that is about that. Now what we need to calculate? Can you give me five more minutes? Okay, so then we can complete this problem. Now what can we do? Now let us consider efficiency equal to 1 minus QC by QR equal to even 1 minus TC by TR. Okay, so that whatever Q ratio and temperature ratio, right? Then let us consider R. R equal to TC. TC is how much? TC T3 divided by T1 we have calculated. Okay. T1 have calculated R. Okay. Then H4. Okay. From this, that factor will come anyhow. We no need to check anyhow. Let us check. Okay. That is reflecting you certain R value. Let it be. Let it be. Now, what we need to calculate? We need to calculate Q34. Q34 means this thing. Q34. Q34 is condensation process, right? Okay. From this ratio, whatever we have considered, that whatever the formula we have taken over here, what is this? This. Okay. This is the ratio only. This is the ratio we have calculated now. Otherwise, nothing. That we are using now in the similar fashion. H4 equal to H3 minus R star Q12 is your input. This Q12 have we defined. Q12 we have calculated somewhere, right? Yeah, Q12. Yeah. Q12 divided by 2. Okay, because when we are calculating itself, we have given over here mass. That is the reason we are dividing over here. Because all enthalpies we are representing over here, whatever this enthalpy, all are specific enthalpies at present we are representing. So, but whatever Q we have calculated, that mass is included. That's what I have divided mass over here. Okay. And now H4 also we have obtained. Where is H4? H4 1180. H4 is 1180, is it? H4. Yeah, H4 1180. Okay. Fine. Now, same like that way, you can calculate V4 also. Okay. Then efficiency obviously equal to 1 minus anyhow R also you can use. Okay. Or as you know, Q34 we have not calculated, right? Q34 obviously. Okay, anyhow, let's use R. Okay. Efficiency equal to 2656. Okay, this is 265, 26.5%. If you want to calculate Q2 from this ratio, anyhow, Q34, Q rejection, these are you can calculate over here. Okay. Q34 you can calculate from again R only. Is it clear about the problem number 5 even with coding? This is your code. This is more simple, right? Because I was explaining to you, that's what it took long time for me. Okay. Otherwise, if you write yourself, it will be only matter of 4 minutes or 5 minutes. It won't take more than that. Okay. Okay. So one simple problem is there. Anyhow, tomorrow let us discuss this, and then after let's go back to transient problems. Those are mixing problems kind of thing. You might have solved in your 11th and 12th standard. But however, let us solve them also. Then that part also would be over. Because if you get one problem, somebody would not be solved that problem in the exam. Okay, then we have to suffer somehow. Okay. So this is our problem number 5. Okay. So please practice in ES as well as please practice manually. Okay. Practicing manual mode itself will be giving you tremendous knowledge. Okay. Yeah. Okay then. Okay. Thank you. Thanks a lot. Because now I have another class, that is combustion class. Okay. Okay. See you. See you in the next class. Thank you.
Thank you, sir.
Thank you, sir.